My name is Casimir Wierzynski, and I lead advanced research in artificial intelligence at Intel. And my team's job is to identify and incubate emerging technologies for next generation AI systems. Now, one of the challenges in this whole space is the fact that modern real-world AI systems aren't just about just chips or just software or just algorithms. The challenge is that to get these things to work well, you actually need all of these elements working together in concert as a system. And the main message I'd like to leave you with today is that a lot of the most important and interesting innovation going on in the entire space is actually exactly in this quest to try to, in this systems engineering quest to get all of these elements to work together well. So the way I'm going to do that is first I'll start with identifying what I think are some of the key trends that are driving the entire field. Then I want to give you a little bit of a mathematical and theoretical framework for thinking about how you would do systems engineering in this space. And then finally, I want to use a case study at the end that really, I think, demonstrates the power of this kind of thinking, of this approach. So clearly, one of the important trends driving the field is just the explosion of digital data. I think we all know this. So for example, 90% of the world's data being created only in the last 2 years. It's kind of staggering to think about it. One way that I like to think about it that kind of gives me a sense of the scale is just between this moment and the time when I finish this sentence, the world will have another 500,000 messages on Facebook and another 40 million emails. Hopefully not all written to me. Another important trend going on in this field is the emergence of this new class of amazing machine called the hyperscale data center. Now, you may say to yourself, well, haven't data centers been around for a long time? Yes, but these modern data centers are qualitatively different from previous ones in at least 2 important ways. One is just the scale, just the sheer scale. So for example, a brand new data center from Facebook these days would cost over $1 billion to build and have over 200,000 servers in it. Another important dimension along which they differ from the past is the sheer amount of connectivity within the data center itself, the volume of data. So for example, the total volume of data that flowed within data centers, inside the data center last year, was 5 times more than the amount of data traffic around the global internet itself. So these modern data centers, they're not just places for warehousing machines or storage. The data center itself, you can think of it as a highly interconnected, highly integrated machine. One of the key workloads going on within the data center, as we all know from being at an AI conference, is deep learning. And some of the features that make deep learning really great for working with this explosion of digital data are, first of all, the fact that you can discover features automatically from data. So your data scientists don't have to kind of hand engineer features anymore. You can kind of automatically extract hierarchical representations of your data. These neural network models are highly expressive, which gives them the quality that when you give them more data, they can actually perform better. So I'd like to kind of unpack these last 2 statements a little bit more. Because they drive these 2 last statements, these 2 qualities of deep learning actually drive one of the important trends I want to talk about today, which is this trend towards bigger and bigger models that use more and more data. And I want to give you a little bit of a kind of a mathematical intuition for why that is. And to do that, we need to take a little bit of an excursion into statistical learning theory. So come with me on the journey, just for one slide. Let's say that you're a data scientist, you're building an image classifier. Say you want something that detects pedestrians. So you'll do the classic data science thing. You need to build up a training set of labeled examples. So you'll have a bunch of images with pedestrians, a bunch of images without pedestrians. You'll train your model, and so without loss of generality, let's call it our small model for now. You'll train your model. You'll measure 2 quantities. First of all, you'll see how well does my model perform on the training set, and we'll call that the training error, and that'll be the blue curve here. And then we'll also test our model on images it's never seen before, and that's the testing error. So these are the two important quantities you care about. And typically, the testing error will be worse than the training error. And that's because the outside world doesn't look exactly like the training set that you have. Your training set doesn't capture the full diversity of the outside world of images it's never seen. As you increase the size of your training set, it becomes more and more representative of the outside world, and these two error rates will converge to some value. Now that's good, except what happens if this kind of asymptotic error rate is not as low as what you need? Either because you can't deploy, it's not good enough to deploy your model, or your competitor actually has a better model, and so how do you get your error rate lower than your competitors? So the next thing you'll do is you'll try a bigger model. Now, one of the things that you may observe when you're training your bigger model is that you'll be very excited to see that on your training set, your training error is much lower than before. In fact, your model may be so big that your training error actually goes to 0. But then when you want to try this model on images it's never seen before, you may find, oh my gosh, it actually does much worse than my previous model. What happened? And so what happened is that in order to realize the full benefits of the bigger model, there is this threshold level of data set size that you need to exceed in order to constrain this bigger model enough so that you can enjoy its full power. And so one way to visualize that is if you superimpose these two curves, you'll see that if you don't have enough training data, you're actually better off using your smaller model. If you have more than a certain amount of training data, your bigger model will do better, and actually you will realize this benefit of this kind of asymptotic convergence to a lower error rate. So the takeaway is that to get lower error rates, to kind of, for your model to be more competitive, you will be driven towards bigger models, and these bigger models require more data. So this is kind of driving this trend. Now, of course, bigger models, more data, this imposes more computational burden on your system. So how are we going to handle that from a compute point of view? Well, here are some, now we're kind of getting into Intel territory. So how do we handle that? One idea is that we can come up with new compute architectures. We can kind of rethink how we do computing. And this is one of the approaches that we're taking at Intel. So we're building, for example, NNPs, neural network processors, which is custom silicon designed expressly for implementing neural network architectures. That's one idea. Another idea is that whatever kind of compute you're using, CPU, GPU, NNPs, or whatever, you want to make sure that these compute elements are fully utilized, that you don't have bits of computation sitting on the chip that are idle because they're waiting for data to arrive, for instance. The other thing that you can do is you can take your job and distribute it across multiple nodes, multiple machines. Another idea is that you can kind of figure out ways of fiddling with the algorithm, either the way that you're training something or the architecture, or you can rethink about how certain parts of your algorithm map onto certain elements of the hardware. The approach that I'm going to advocate for in this talk is actually all of the above. In other words, kind of take a systems approach. Now, okay, that sounds good in theory, all of the above. How do I do this? I'd like to give you a little bit of a mental model for how a systems engineer might think about turning all of these various knobs to get the best performance out of their system. So for any kind of running system, an engineer will look at it and say, okay, well, I've built my AI system. It's kind of deployed at some scale. How come it runs at a certain rate? It can do a certain number of inferences per second, let's say. How do I get that number up? What's preventing me from increasing the throughput of my system as it's currently designed? Do I not have enough compute power? Am I not able to move data around fast enough on my system? Am I perhaps using the wrong algorithm? Or am I using the right algorithm, but my implementation of that algorithm is not particularly good? So how do I kind of figure that out? To do that, I think a nice way to look at all of these questions together is something called the roofline model. So it's a graph where you can, on the y-axis, you represent compute speed, operations per second. On the x-axis, it's useful to plot some quantity that's called operational intensity, which kind of represents the ratio of compute to communication. So for any given, on average, for a byte of data that the system receives, how much compute does it do on that byte of data before it moves on to the next stage? If you represent things this way, then you can start to represent certain hard constraints in your system. For example, in your entire system, you only have so much compute capacity. Suppose that every possible thing that can compute in your system is just going at 100%. How many operations per second could you achieve? And that's a kind of an upper bound on the compute side. You can also you can look at a hard constraint of how fast can I move data around within my system? What is my kind of communication bandwidth within the system? That constraint corresponds, based on these units, that constraint matches a diagonal line. So any kind of system that you can achieve, any implementation you can achieve has to sit at or below both of these curves. Now we can look at different algorithms. Let's consider two algorithms. The operational intensity of an algorithm is something that falls out of the math of the algorithm itself. It's independent of the implementation. So on the x-axis, you can kind of draw vertical lines that correspond to different algorithms. And then finally, we have specific implementations of those algorithms, so those dots there. So that, it's kind of like you live here. Your current system may be one of these two dots. So now that you've done that, you actually have a kind of an interesting, there's all kinds of interesting things that you can read off of this graph. For example, you may say, okay, well, our implementation of algorithm 1 is not as efficient as it could be because it's not hitting this upper bound. And we can also say that when it hits this upper bound, what will be limiting the speed of the system is not the amount of compute available, it's actually the speed at which I can move data around. Whereas for my implementation of algorithm 2, it's also not as efficient as it could be. And when I do make it as efficient as it can be, it will exceed the capability of algorithm 1, but it will be limited by the amount of compute power within my system. So you can see this is kind of a nice way of seeing all the different trade-offs and the variables. And then finally, you can identify that there's this sweet spot where the two constraint curves meet, this green dot. And that's kind of the nice, I say sweet spot because that's where the rate at which you compute, the maximum rate at which you can compute exactly matches the rate at which you can move data around. So those two are kind of perfectly coupled. So we talked about all the various knobs that are available to the systems engineer to turn. One of the important knobs to turn is the number of machines that an algorithm is running on. This is one that has been used quite a bit lately. So we say that these algorithms are becoming more and more distributed across nodes. And this is just kind of a historical view of this phenomenon. So back in 2012, there was an effort to distribute deep learning across many thousands of CPUs. And that was because at the time, GPUs had certain memory limitations that they then overcame. And so once they did that, then in 2013, people started using small numbers of GPUs to train their models. And since then, the trend is to kind of spread work across more and more machines of different types, and sometimes a mix of types. So let's think about how do you distribute a deep learning workload across machines? What are your options? Well, you can split up the model, or you can split up the data, or both. And so let's look at the consequences of some of those decisions. So if you split up the model, that's kind of what's going on the left side of the figure here. Your model itself is now spread across multiple machines. the consequence there is that you're going to incur these communication costs between different parts of the models that sit on different machines, right? Wherever the model gets split across, there's communication traffic. If you split up your data, let's say if you train various workers to learn from different subsets of your data, then, and that's the situation that's going on the right here. Now you've got, besides the compute costs of kind of represented by the blue parts, you also have communication costs. You're going to be communicating weights and weight updates to some kind of central parameter server. You're also going to have some storage. You're going to have to think about how you organize your storage too, because you can see these white cylinders at the bottom here. These represent your data stores. You've got communication from your data store to these workers that are learning, that are doing the learning on subsets of your data. So besides computation, we're going to have to think about communication costs, and we're going to have to think about how we organize storage. For storage, we can think, well, it would be nice if all of the data were as close as possible to the compute. So we need to think about the density of storage. So let me talk about these two things in one after the other, communication and then storage. So I mentioned earlier there's a lot of traffic going on within the data center itself, and this is something that we in Intel have been working on. A fair amount of it is optical. So there's right now in data centers very sophisticated interconnect systems within racks, across racks, and multiple levels of switches. One of the teams at Intel that I really enjoy talking to and that my team interacts with quite a bit is the silicon photonics team. So they've been using silicon photonics technology to build optical interconnects. And what they do, roughly speaking, is that they use the same fabrication techniques that people use for electronic circuits, but they use them for light circuits. One of the important capabilities they've been able to develop over the last many years is to be able to fabricate lasers directly onto a chip. And so what that enables you to do is not have to rely on having to bond an external laser and kind of mechanically couple it to your chip. You can build the laser directly onto the chip. And what that means is that now you can have much higher levels of integration for these optical circuits. And you can even imagine that someday that the level of integration would be enough that you could have a very high-speed optical interconnect going directly into a deep learning accelerator, for instance. Now I want to talk a little bit about storage too. So we've been thinking about the storage problem as well at Intel. And Intel makes SSDs, makes a lot of SSDs based on a couple of different technologies. One is NAND-based, and the other is 3D XPoint. I want to talk about 3D XPoint in particular because it's just very cool. It uses this kind of, it gets its name from this 3D crossbar nanostructure that it's made out of. So let's say you were the size of an atom. This would be a really fun jungle gym that you could play in. Some of the qualities of 3D XPoint are that it's non-volatile, it's denser than DRAM, and faster than Flash. So when we recall the case where you wanted to have your training to be distributed and you had your training data across these various cylinders, data density and the speed at which you can access your data are going to be very critical variables in systems like that. We can also build this storage in really cool form factors, and the one that I want to highlight in particular is this one called the ruler at the end. So it's literally like the size of a ruler, like the kind of thing that you would discipline someone with, like or measure things. So it's about 12 inches long, and it's designed in this way so that in the data center, you can take a 1U server, so something about the size of a pizza box. You can slot all these little rulers in there, and now in this 1U form factor, you've got a petabyte of storage, which is a huge it's incredibly dense amount of, it's a lot to store in that space. So to give you a sense of a petabyte of data, let's say you wanted to have a video collection, a HD video collection that you wanted to just sit there and watch, without having to get off your couch. This would give you enough to watch videos between now and the year 2088. Okay, so we've talked about trends. We've talked about kind of a theoretical framework for how you do systems engineering and AI systems. I want to finish with a case study that I think shows the power of the kind of cleverness and the results that you can achieve when you put some of this knowledge to work. And to highlight that, I'm going to take the example of, I don't know if you saw Greg Brockman's talk today, but this idea of using reinforcement learning to achieve superhuman performance on video games. So you can use reinforcement learning to design AI systems that only by looking at the screen of a game and manipulating the control and following the score of their own game, these agents can learn to play non-trivial video games better than humans can. And one of the important things about systems engineering is that the systems that do this have been able to improve in training speed by a factor of 50 just in the last 3 years. Just by kind of tweaking aspects of the architecture, the hardware, the software, the algorithm. So I'll show you how this progression came about. So in the beginning, we had this kind of this seminal paper from DeepMind in Nature 2015, where they introduced this concept of the deep Q network. And the innovation there was that they have this, they're using approximate Q learning to do the learning. They're using a convolutional neural network to implement the Q function. And then an important part of the training process is that you needed to have this concept of a replay memory. So your AI agent was not only kind of trying out certain things in the game, but it was also keeping a diary of things that it had tried and what happened when it tried these things. So that then when it needs to update its policy in order to play even better, it can make those updates not just based on what it most recently tried, but it can also grab random pages from its diary and make sure that it's not overfitting recent experience, but it's also keeping its past experience in mind. So that's an important component to make the whole thing work. And that took about 8 days to train. The next step was that some of the same people figured out, oh, well, we can actually distribute this workload across multiple machines. We'll use roughly the same algorithm, same RL system, but we can now have, instead of one agent, we can have multiple agents. Instead of having one learner, we can have multiple learners. And there's still this idea of a replay memory where these various agents need to store their memories in some big bucket, and then other learners will take random subsets of those experiences and learn from them. By splitting things across multiple machines, they were able to cut the training time down in half, which is great. They had to use 100 machines to do it, but still, if you care about training time, they were able to cut training time down in half. Then, just a year later, some of the original authors of the DQN paper figured out, this replay memory thing is creating a lot of communication costs. There's a lot of network traffic where all these learners have to kind of grab experiences and do some learning based on these experiences. What if we take all of the learners, and instead of having them on separate machines, we put them on separate cores of a multi-core CPU system? And instead of having an experience bucket where people kind of throw all their experiences in there and then other agents come and grab from there, why don't we have a whole bunch of agents starting at kind of independent times in the environment, so all of their actions, they're all kind of exploring different parts of the environment with slightly different policies at the same time. Doing this generates a whole set of independent experiences that you can think of each round of experience from all of these workers is just as good statistically as taking a batch of experiences from this replay memory. So if you do that, now you've changed the communication cost quite a bit in this system. By moving everything onto multi-core, now communication is happening over shared memory instead of over a network. When you do that, you're able to reduce the time, the training time, by a factor of 4, and you're running things on a single multi-core CPU now. So this is starting to give you a sense of the power of systems-level thinking. And then as a kind of a final flourish, some recent work from Uber AI labs, they figured out, they kind of attacked this problem from 2 more angles. They looked at a different way to do the optimization, and they also kind of figured out some way to do some fine-grained scheduling of tasks across the CPU cores, and they added a GPU to a desktop machine. And when they did this, they were able to cut training time by another factor of 6. So in summary, we looked at some trends where models are getting bigger and they're consuming more data. Another important trend is that because of this increased computational load, these models are getting more and more distributed. We saw a theoretical framework to think about this kind of complex interplay between what happens when you change certain aspects of the compute, of the interconnect, of the storage, of the algorithm, and the fact that you really need to keep all of these things in mind at the same time, because there are these nonlinear interactions between making these design choices. And because of that, I'm advocating a systems approach to designing real-world AI systems and co-design of all of these aspects. So thanks for your time today, and I think I have some time for questions if you want.
Yep.
Yeah.
Let's then go to the speaker. And do we have any questions?
Yeah.
How is AI computation different from HPC? I know it's also a very high intensity kind of computation, but from an architectural standpoint, how is that different? Can I leverage existing HPC environment to do my AI work?
Yeah, so the question is, how does AI differ from HPC in terms of a compute workload? That's a great question. So Intel has done a bunch of work with some of the big HPC centers to run deep learning workloads on HPC infrastructure. So yes, and a lot of this kind of roofline thinking, it comes from this HPC world. One way in which it can differ is that in a lot of cases, particularly when you're doing inference in an AI context, the amount of precision that you need is much less than in an HPC workload. So you can get away with 8-bit precision or even 4-bit precision, whereas HPC often you want like double precision type things for simulations and things like that. So that would be one point of distinction.
So can you give us some idea of the cost differential? You were talking about the Optane machines with up to a petabyte of storage, presumably with a bunch of GPUs and CPUs on the same 1U box. How does that equate into a pricing compared to a multi-machine environment?
So you're talking about the stuffing a bunch of rulers into 1U,
Yes.
and how does that compare to?
What's the cost differential between that and the common way that it's done today?
Yeah, so I'll dodge your question a little bit, and then I'll try to answer some other aspects of it. So I'm the research guy. I'm not the pricing guy, but there's I think you physically couldn't get hard drives into that form factor at all. So if you care about being able to get as much as possible within that rack, because rack space is expensive, because cooling is expensive, because of so on and so on, then there may be no other way to kind of achieve that form factor. Now, yeah, I don't have a kind of a well, but it's a complicated question of, yeah. It's not just dollars per byte. It's dollars per byte per cubic foot per, yeah.
Could you talk a little bit about the landscape for hardware accelerators, especially sort of in the light of what you've been talking about in terms of systems thinking? Like, do you see hardware accelerators as being as important as interconnect and storage, or like, which would you look to first if you were sort of taking on just a de novo, HPC cluster kind of setup?
Yeah, so hardware accelerators will clearly be important in this landscape, but I think in terms of like what's the first, like if I had a working system and I wanted to make it go faster, I would think about this roofline model. Like it could very well be that the thing that you're trying to do is actually not constrained by compute, it's constrained by communication bandwidth or something like that. So
Are there any like hardware accelerated trends that jump out to you as being
well, I'm particularly keen on the stuff that we are working on. There's a big diversity of, we're kind of, I would say there's just so much interesting work going on in hardware architecture, like computing architectures right now, broadly speaking, that it's just great to see so much diversity. And we're clearly making our bets in certain ways, but it's very interesting to see the diversity of it. Yeah.
So how do you differentiate between Optane and SSDs?
Well, so SSDs can be made with the 3D XPoint, or they can be made with NAND. And in some cases, you can actually put the two together and have kind of like a hierarchy between the two.
So which one is faster, like Optane or SSDs? Or we have to have both of them together to work better?
You can, either one of them works fine separately. One is denser. The 3D XPoint is faster than Flash.
Okay.
Yeah. We can talk more after the talk if you want. Yeah.
Hello. I have a question about compiler. So I used to run HPC in the pharma domain a lot. And we, at Big Pharmas, we used to support applications using Intel compiler, MKL, etc., to the point that it's too much hassle to support. So my question is, what's Intel's efforts in open source things like GCC? Do you guys contribute to GCC in addition to the ICC? Because just to support ICC is not scalable. I understand, lots of people are researchers, they have the source code. And in lots of cases, we get out-of-box programs. Mm-hmm. That's a challenge.
Yeah, so the question is about compilers and how do you, if you have got some big heterogeneous system like this, how do you write software that targets this kind of mix of hardware and so on? So the strategy that we're taking, and I can point you to some open source repos and materials, is that because there's all these various high-level languages in which people want to describe deep learning in different frameworks and TensorFlow and so on, things like that, and this variety of hardware targets that people want to run on, the way that we're attacking this problem is to define an intermediate representation. We're defining a way that people can. We're building tools that will allow folks to take all of these various high-level descriptions of deep learning tasks and represent them as a computational graph, so kind of a more abstract form. And then for various hardware targets, people can then write so-called backends, which will then generate efficient code from this intermediate representation to whatever hardware they want to target. Does that make sense? So it's a little bit like a LLVM type model. Okay. Yeah, that makes sense. And the name of the compiler is called ngraph. So I can point you towards ngraph.
Okay, thank you.
Yeah.
Do we have more questions? I think the last one.
How does systems approach to kind of designing some of these, approaching some of these problems? Average mid-sized company, right? And if you're deploying a machine learning model, you probably go to the cloud. right? So how does that kind of figure with the systems approach where you're thinking about hardware optimization as well?
Well, I think a number of you're talking about like public cloud type, yeah. Well, how you organize things on, let's say, AWS and which, buckets you pick and how you design virtual networks and so on. There are some elements of this that you can control if you want to go. Different public cloud providers will allow more granular control of some of the elements. If you're just kind of using a straight kind of machine learning API, then you may not be able to control what's under the hood there. But yeah. Thanks, everybody.
Okay, let's thank us again to Casimir for a great speech, and then I'll see you in the next session.